Thanks for listening to my talk. I'm going to talk about the stability of superconducting strings. This is based on the work I with K from Chicago, and Xu is my student, and Feng Wei is the postdoc in our group. The idea is originated from thinking about whether superconducting string can be a dark matter. But we immediately faced the question whether superconducting string is stable. I also even asked my colleague P.S. Kiwi what's his viewpoint. He told me it's an open question, and he has a question about why at the classical level superconducting string is stable. I will address this question in my talk. Let me get started, and here's the outline. I will start with introduction and very briefly introduce you about the cosmic string and then the superconducting string. And over here, I focus on the fermionic superconducting string, and it can be extended for bosonic. The second part talk, I will have a short review on the Volton stability. So the Volton is the stable configuration of superconducting strings. But whether it's stable, as I said, is an open question. There's I only list a few of them, and here, for example, quantum tunneling. And Witten, in his seminar paper, claimed there was some certain energy, the tunneling will happen, and Volton is unstable. But in other paper like Barr and Martinson and they're thinking about the energy can be higher, especially in the book by Vilenkin and Charlotte, and claim that they agree with the latter statement. Even recently, there was a decay due to the fermion in the superconducting can decay to the standard model particles, and which is a model dependent statement. But there were two groups give two reliable calculation. Their results are different. How do we understand them? There are also other disagreements I will list later. So the main part of the talk will be discuss the Volton stability at the class level, then the Volton stability from quantum tunneling, decay, and scatterings. Let me start with introducing the global strings. Let's start with global U1 symmetry, which can be spontaneously broken by a valve of scalar field. The scalar field charged under this U1, and the valve is 1 over square root 2 Fa. Then using this valve, you can build a vacuum. It's just a trivial vacuum, and everywhere is this vacuum expectation value. Or you can build a classical solution. It's a global string solution. It's like at infinity, you have the vacuum and plus e to the I theta. Theta is the azimuthal angle, which we call as winding number. It's winding number 1. At the origin, and you see the scalar field becoming 0 and symmetry is restored. And you can build this string solution. The string width is roughly about the inverse mass of the scalar. And you can compute intention. It's not the infinite energy, especially when you cut the string as an IR cutoff, with string has some distance between the other string. So you can calculate the gradient term, which is gives a pi Fa square, and there's log divergence. Then what's superconducting string? It's very natural to add a fermion in the system. Let's say I have a global U1 charge with a chiral fermion. They have kinetic time here. Also, they have Yukawa-like coupling. The coupling is y psi, and they couple to phi. From the index theory, so in the background of string, they should have 0 mode. Or you can just complete it explicitly. And then first you decompose the fermion solution into the transverse part and the longitudinal part. The transverse part is satisfied the let's say Schrödinger-like equation as h hat times psi equals 0. This is a time-independent Schrödinger equation tell you the energy is 0 energy solution. And when you go the transverse direction, you will find that it's equivalent to a massless mode propagating along the string. It's a left-moving massless mode. It's let me emphasize also it's antiparticle also left-moving. So if you have an empty string, how do we charge it? One way is applying electric field along the string. The Fermi 0 mode current is generated. But immediately you have a problem. It's like when you have electric field, then the Fermi number is not conserved along the string. And this actually can be understood different way. One of the way is the anomaly inflow. It's because the full system is 4D. And you can compute in the Goldstone-Virchow anomaly. The currents, it can be computed by the triangle diagram, and one of them is just the current J mu. The other vertex is coupled to the gauge feed A mu, and which is related to E feed background feed, and then the other vertex is coupled to the U1 seed angle. Then you will find that there was an induced current along the string, and the divergence current is zero outside, but it's non-zero inside, also proportional to electric field E. And here I assume the string is infinity. And from here, you immediately conclude that this is superconducting. And in the sense that normally conductor is like current proportional to the electric field. But here is like current increasing proportional electric field. Even after the electric field turns off, and your currents will persist. And there's a Fermi zero mode always running along the loop. This is superconducting. The superconducting string is a phenomenology rich because there's cosmology. You can produce this superconducting string coming from phase transition, and then they can collect a lot of fermion by the electric field in the electric field coming from the plasma around the universe. So the plasma is we know that when we the early universe has high temperature, the plasma induces electric field. The temp T here is the temperature. The electric field amplitude is roughly T squared, and the coherent length and the coherent time is about the inverse of T. Imagine you have a very long string, roughly about the Hubble radius, and then they will have experienced a lot of random work, and from the electric field, there was an electric field up and down, and because the electric field up and down, but the net charge, they will generate charge along the string. The net charge cannot be zero. It's basically a random work, and you can estimate for at a temperature 0.1 GeV, for example, if you have a long string, and they will be the electric field can generate like charge 10 to the 19. It's a very large charge, and this is how a superconducting string can be have a lot of Fermi currents. As I mentioned in the introduction, there is a stable configuration called a photon. To understand the photon, and we should think about that there is a potential, two potential over here in the string. One is the string tension. The string tension, or we say string mass, give one potential, and we computed tension before is roughly pi Fa square. Fa is the VAV. And if the string is longer and mass is larger, so there is a potential proportional to the length of string. But let's imagine the fermion charge is fixed. And if you make the string smaller, actually Fermi energy becoming larger and larger because the momentum of energy are quantized in the small loop. And then you easily convince yourself the potential from the Fermi zero mode is inverse proportional to 1 of L. One is proportional to L, the other is inverse proportional to 1 of L. Therefore, there's some stable point. We call it we call it the critical length, or it's the photon configuration. The important question is photon stable, especially my first goal, as I mentioned, is how to build a dark matter. And to have it, let's think about is photon stable. I want to thank Pierre raised this question, and there's no study, as far as I know, there's no study in the literature. It's the classical dynamics can make it overshoot. Let's imagine you have a string starting from the very some position of the potential, they were rolling, and actually they were not relaxed to whether they were relaxed to the critical point or they were overshoot. This is a very hard question if you want to do theoretical calculation because of the global stream property, but you can maybe rely on simulation. Second is the quantum tunneling. The quantum tunneling is like a zero mode that can convert to excited state. So we can argue that there's a critical energy, one energy is larger than m psi, and then the zero mode energy is big enough they can escape the string, and this is a very reasonable argument. But from other work, you can see that, and they think the critical energy actually much larger. The problem for this critical energy proposed by Witten is actually this energy is actually smaller that make this is actually close to here. It means that most of the photon will be unstable. And then there's another calculation related to is model dependent, depending on the zero mode coupled to the standard model particle. Here I give example like coupled to the Higgs and the quarks. And then the zero mode will decay. nothing prevents its decay because the vortex is there. There are two calculations. One is say that there was one way to think that zero mode will decay, and the other group by EB and others, they're thinking that there was also oscillation of the stream mode, and there were the scalar, we can think about a scalar oscillation. They were scattering with zero mode and produce H and Higgs and quark. Their calculation all reasonable. I follow their result, and but they give different result. Finally, the last thing is scattering surrounding particle is proposed by the people in this paper, and because the cosmic string is charged, they will pair produce electron and positron. The electron will be very high energy going close to the string, and they will scatter with zero mode. And if the electron or positron energy is big enough, they will kick the zero mode out. This is the model independent statement, and we want to address the four of the questions. So let's look at the first one, the photon stepping from string dynamics. And we want to emphasize that this is a global string. First, the global string will radiate. As we said, they will radiate. It's a global string coupled to the Goldstone mode, like axions, and they will radiate. So the string initial energy is not equal. We are not equal to string final energy because they keep radiating the axions. If near the critical length here, or the bottom size, the kinetic energy, if it lose the energy big enough, it can actually close the stream mass, and then they will be relaxed to this point. Here's the one simulation without the back reaction. It's like you have a string loop, they will just collapse and bouncing back. They will never stop. Or you can including the axion radiation in your simulation, not similar number global string, but similar global string. You will feel like there's no bouncing back. They just keep losing axion, and they will make the string don't oscillate so fast. So this is our simulation. We're starting from some loop radius, and they will just radiate the axion, and also because of tension of string, they will shrink. But when they shrink, they will not go faster and faster. Actually, we measure the boost factor. They are all along the order 1, becoming asymptotic. Therefore, we conclude that from our simulation, they actually because of radiating axion, they can relax to the critical point. So I will not talking about quantum tunneling in the beginning. Let's talking about model dependent way. It's like zero mode decay, because this method is very generic, can be applied to quantum tunneling. So zero mode decay. So here you can see a string, superconducting loop over here, and zero mode is inside the loop. They can decay to the quark and the Higgs. I want to make an assumption like the string is infinitely the same, and because the really most important thing is the curvature. It's nothing. Most of the time, it's not the width of the string. And then we can reduce the effective coupling to adding a delta function. Delta function here is if I think about a string along the z direction, it's just delta function delta square xy, and this will simplify the interaction term and make the calculation easy. But then the string is actually it's not in a straight loop, and it's not straight, so we have to introduce the worksheet 2D metric to do the matrix element. Here we found that because of time translation event, there's energy conservation, we understand, but because the string break the translation symmetry and there's no momentum conservation. That's quite different from asymmetric calculation before. But instead of when we're using the 2D worksheet method, you can easily get not a delta function, but a Bessel function. N is E times R, roughly is the charge of the, E is the energy, R is the radius, is roughly the charge of the superconducting string, the Fermi charge. But there's a way to understand this. Just because of we choose a circular loop, actually, this just means the angular momentum is conserved. And because to make the energy conservation and angular momentum conserved, they will focus the cone in a very small range. It's roughly E times L. L is the length of the string, and to the power of -1/3. And then the zero mode two-body decay is also suppressed by the phase space. And this result is consistent with one of the computation is by Hitoshi and etc. But there was a two decay process, right? As I said, there were two computation. One is by Fukada, Munaha, and Murayama and Taylor. And they think that the zero mode always follow the stream profile, and the zero mode decay to the Higgs and the quark, and all results are consistent with them. And then we find that there was other thing, the other group, EB and their group, is consider the scalar field oscillating, and they were scattering with zero mode. And using effect field theory, we find that we can combine the two processes together, and they all can have in the same framework. And also the first one we find that is always dominant, and the second one is when we using the quantum mechanics trick, we find that this is just sudden approximation, means that zero mode doesn't you have suddenly change of string, and the zero mode doesn't follow. In this way, you have this scattering, and all conclusions, the two processes coexist. But in most cases, the adiabatic process is dominant. Okay, let me talk about the second one is the quantum tunneling. The quantum tunneling is, first we want to say that the zero mode states are not bounded. In this sense, when we solve in the time-independent Schrödinger equation, this is just the time-independent Schrödinger equation for the fermion, we found that when energy is larger than ampersand, there's no solution like decay at spatial infinity. This means that a stable bound state doesn't exist. Or in other ways, the zero mode is a local bound state where mixed with excited. So we do agree with Witten that in this sense, energy larger than ampersand, there was a mixing. The mixing will trigger the decay, but how do we compute decay? We still need some formula. So what we rely on is two kind of method. One is all S-metric computation. The other is just classical calculation. So the S-metric calculation, if you remember, this is just the Bessel function. The Bessel function tells us there's angular momentum conservation, or the rate we calculate is n time exponential to the some power. It means that the tunneling only occurred at critical energy, not at ampersand. It's square root ampersand times r times ampersand. And all calculation is justified using the energy and angular momentum conservation. Using these two arguments, the classical derivation, you can reach the same result. Due to time reason, and I don't show you the classical derivation, the derivation from classical physics, but they are consistent. The summary is like a written claim like the critical energy should be larger than ampersand. We agree, and while the other people claim that energy is larger than ampersand square are using just the momentum uncertainty and energy conservation. This is not precise. So our result using S metric and the classical argument, we get a different result from the two group. Let me go to the last one. It's becoming model. It's also another model independent constraints from the photon. We don't need to introduce couplings, and because the surrounding particle will scattering with the zero mode. So the charge of the superconducting roughly like you can think about 2D atom, and the energy of E plus E minus. Then you have Fermi zero mode over here. This is right line is Fermi zero. They are charged, and they will have a electric field. It's proportional one over rho is the radius, and because the electric field is very large near the low mean, the minimum of the radius, and they will when they large enough, they will pair produce E plus E minus, and also accelerate the E plus E minus, E plus or E minus towards the zero mode, and they were scattering, and zero mode will unstable unless your Fermi mass is super large and larger than the probability value. So this way we agree with this computation. It seems like from this we almost conclude that the Fermi zero mode is unstable, but there was one we missed one possibility is like the width of the Fermi zero mode. There was another possibility. One, the scalar mass much smaller than ampersand, the width of zero mode is much bigger, and the low mean, the minimum radius becoming larger, such that the electric field cannot be very large near the boundary, and it will give much less energy of the electron, and we find that at this certain primary space, there was a stable zero mode. Let me summarize. I introduce you what's superconducting string, and I tell you that there was an open question before our study. There was a photon stability from string dynamics. We did the first simulation to study this. We find that the photon is stable, and the photon stability from quantum tunneling. We have there were two arguments before, but we use S-metric calculation and classical argument. We give the same different result, but we reach the same result using the two methods. And for the decay is model dependent same, and we find the two previous calculation is just the focus on two region. One is adiabatic, the other non-adiabatic. And the last one for the scattering surrounding particle, we find that for wide zero mode, it still can make photon stable. So our next project is whether we can build a dark matter model to have a stable photon as a dark matter candidate. Thank you.